Here is the next example on the polar plot. So the given example is a open loop transfer function of a unity feedback system is given by g of s equal to 1 over s times 1 plus s square. Sketch the polar plot and find the gain margin and phase margin. So basically what he's saying, he gave us this g of s. Okay, that's an open loop transfer function. And he said it has a unity feedback, so that's a unity feedback. So here u of s, y of s. That's a complete system. So here he's asking about find the gain margin and phase margin of this given g of s. Okay, so here from the previous video, you know that as long as we know the type and order of the system, we can simply draw the polar plot, but we cannot, by using that simple plot, we cannot find gain margin and phase margin. We have to follow the method, following method to find those gain margin and phase margin. I will talk about what is phase margin, gain margin somewhere in between in this video. Now, so what is this type of the system? We know type is based on how many poles. So this is a characteristic polynomial. If we make it equal to 0, we call it as characteristic polynomial equation. This gives us the poles of the system. Okay, now how many poles are there at the origin? That gives you type. So here we have one pole, so it's a type 1. So if we have 2 poles at origin, we'll say type 2. No poles at origin, type 0. And order of the system is nothing but it tells you what is the how many poles are there, total poles, total number of poles in the system. Order is nothing but total poles of the system. So it's a third order. So third order is right there. So basically when we draw this line is going to start somewhere here. Okay, somewhere here, and it may end like this. Okay, I draw the straight line. It need not to be a straight line. It could be something like this. Actually, second one looks a little bit better. Okay, so this is the polar plot. Okay, this y-axis and this plot is not going to meet anywhere. Probably it's going to meet at the infinite, because whenever I substitute omega equal to infinite, then only this value whenever I substitute omega equal to 0, this value equal to infinite. So this line is going to meet at that distance. Now what we're going to do, so this is just a model, but as I mentioned, we cannot find gain margin, phase margin from this. So we have to find first what is the magnitude and phase angle. The formula for magnitude, so I'm going to substitute here s equal to j omega. We know that s equal to j omega. I'm going to substitute s equal to j omega here. I will end up with 1 over j omega times 1 plus j omega whole square. So the magnitude equal to, I simplified it here, but when you write down the magnitude is going to be magnitude equal to 1 over square root of, so here I have real part as 0, so 0 square plus omega square times square root of 1 square plus omega square. Okay, and I have whole square, so it's a whole square. This is the magnitude. So when we simplify this, I'll end up with that equation. If you have something in the numerator, we will do the same thing. Real part square plus imaginary part square root of, that will give you the magnitude. And the phase angle is theta equal to minus tan inverse of imaginary over real. So since if it is in the denominator, we'll take the minus. If it is in the numerator, we'll take the plus. Similar to the Border plot, what we did in the Border plot. So these two terms are in the denominator, so I'll take minus tan inverse of omega over 0, because there is no real part, minus 2 times, because this is square, that's a square, so minus 2 times tan inverse of omega over 1. So tan inverse of omega over 0 is nothing but minus 90 minus 2 tan inverse of omega over 1. Now Here the magnitude doesn't have any units. Okay, omega is in radians per second. Okay, now what values I'm going to choose this omega? How did I choose this omega values as 0.3, 0.4? These numbers, actually I have a little bit more, okay, up to this. So how did I choose this number? I chose those numbers by inspection. My main goal is I'm caring for this number, which is approximately equal to 1. As long as magnitude is 1, that omega value is needed. That's all I care for. And then the remaining values, probably 2, 3 on the left hand side, 2, 3 on the right hand side, I'm going to pick them up, the omega values, so that I can draw the whole plot. Okay, so how did I choose the omega value? So I wanted to have magnitude is as 1 at one point. Okay, so you substitute omega value in this magnitude in this equation, so where it became 1. So that's the omega value, and choose left side couple of values, right side couple of values. If you have 5-6 points, I think that's good enough to draw a plot. So to get that 1, what I did here, by inspection, I just substituted 0.5, 0.6, 0.7. When I substituted 0.7, I end up with very close to 1. Okay, so I chose 0.7, and then 0.5, 0.3, 0.9, something like that. So at 0.3, substitute omega equal to 0.3 in the magnitude. When I substitute 0.3 in omega value, I ended up with magnitude as 3.058. And phase angle, when I substitute 0.3 here, so tan inverse of 0.3 times 2 plus 90, altogether this angle is total minus 123.39. okay, 3 is a little bit bigger number. When I'm indicating that in the polar plot, I don't have 3, so that's the reason I chose 0.4. I use different color because when I'm drawing the polar plot by using red color, I want to have one more point, so I chose 0.4. But other than that, it's these values I got them by directly substituting omega value in the magnitude and a phase angle. Okay, I substituted up to 2. I have a little bit more values, but as I mentioned, as long as you have 5-6 values, that's good enough to draw the plot. Now, what is the polar plot? This polar plot is going to be a little bit different. Okay, it's look like a circle. Let me make it a little bit bigger. Okay, so here this circle, let me use different color. Okay, if you look at the circle, the magnitude of the circle, I'm choosing that as 0.4. Okay, so here it is 0.4, here it is 0.4, here it is 0.4, this is 0.4. Okay, so I chose this as 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. Okay, so those are the values I chose. As I mentioned, I care for 1. That 1 is called unity circle. So here is 1. This is called unit circle. Okay, this is called unit circle. Okay, now, and the graph itself gives you angles. So this is 0, minus 30. So that means this is minus 10, minus 20, minus 30, minus 40, minus 50. So there is one line in between. So I can choose minus 35, minus 45, minus 55, like that. Okay, so this is the polar plot or polar graph basically. Now I have the magnitude and phase angle. Okay, so now at 0.3 I have 3.058. Do I have the 3.058? I don't actually. I can have it. Let me represent that. So if you look at here at 0.3, omega value as 0.3, I do not have omega value in this graph. All I care for these two values, magnitude and phase angle. Okay, so 3.058 minus 123. So that's 2. No, I will not have that. 2.2 That's 2.4. Yeah, I cannot do that. So let me choose the next one, which is at 0.4. I have 2.15 at an angle of minus 133. This is minus 133. So how did I choose? Magnitude is 2.15. Okay, so if you look at here, this is 2. Okay, so 2.15 is 2.2. So 2.15 very close to 2.2, right? So it's somewhere here. What is the angle? 133. So this is 130, 135. So it's going to be somewhere here. Okay, so 2.15 at an angle of 133. 2.15 at an angle of negative 133. Negative 133. So these are all negative angles, by the way. Okay, negative 120, negative 150. Okay, so negative 133 is right there. Now the next point is 0.5. At 0.5, so I don't care about omega value, I care about these two. 1.6 at negative 143 degrees. So 1.6, so this is 1.6 at negative 143, so it's negative 145 here, so 143 is right there. Like that, I chose these dots. Okay, so as I said, all I care at unity, I mean 0.958, approximately 1 at minus 160 degrees. So this is minus 150, minus 160 degrees, so that's minus 160. It has unity. Okay, now I'm going to draw this graph line. Okay, make sure you connect the correct dots. Okay, there you go. Now this is my final graph. Okay, this is my final graph. So if you look at our final graph, it's almost look like the approximate graph. Okay, it started in type 1, ended at the third order. So you can see, I mean, this at the end, probably this is going to come closer to the y-axis. Okay, when we go bigger numbers. So that's the reason it just look like it's far away, but it's a type 1 order 3. Now the question he's asking about, what is the gain margin and phase margin? So the definition for the gain margin, phase margin. So before going to the gain margin and phase margin, we need to know phase crossover frequency, gain crossover frequency. So here phase crossover frequency is, it is the frequency at which the phase of GJ omega is at 180 degrees. So the crossover frequency is, this is minus 180 degrees. So this point is called phase crossover frequency. Crossover frequency. Okay, now the gain margin is nothing but gain margin. It is defined as the inverse of the magnitude of GJ omega at phase crossover frequency. What is the magnitude at this point? So if you look at here at that point, let me use different color. Okay, that is between this line and this line, isn't it? So between 0.6 and 0.4 look like, I can say in the middle, like 0.5. Okay, so the gain margin equal to 1 over 0.5. That's 2. There are no units for this magnitude, so it's just 2. That is about the gain margin. Now phase margin. So for the phase margin, find out what is the gain crossover frequency. It is the frequency at which the magnitude of GJ omega is unity. So where do we have the unity? So right there. Okay, so magnitude of this graph is unity at this point. So what is the angle there? I would say, I mean, actually we found that value at unity, it's approximately minus 160 degrees. Okay, so the phase margin gamma equal to 180 plus 5 GC. So gamma phase margin gamma equal to 180, positive 180 plus 5 GC, which is, what is that value? I would say it's a minus 160 degrees. Okay, we're drawing approximate value, so definitely we'll have a little bit of error, so don't worry about that. Okay, this is the phase margin. So gain margin is 2, no units, or you can say 2 units or something like that. No unit for that gain margin. Phase margin is 20 degrees. So when we do it in the Bodo plot, it's decibels, okay, degrees. But here in the polar plots, we don't have any units. Its gain margin is just 2. Okay, that's about the polar graph or polar plot. I'm going to solve one more example in this. Thank you.